building blocks of electronic devices. Uh, so, for example, if you remember, BJT is made out of two PN junctions essentially. So, if one understands the PN junction, the diode properly, the physics of the diode properly, then uh, understanding other things become easier. Also, the MOSFET transistor, which is I would say uh, the most important modern day electronic device, is also made out of combining several semiconductors together. Okay, so that way, spending time on understanding PN junction, its basics is worth it, because once if this is clear, then all other things are easy to understand. And apart from its basic physics, we also went through the IV characteristics of the PN junction, both in forward bias and in the reverse bias. And if you recall, ultimately uh, it is about controlling the diffusion of majority carriers and drift of minority carriers, this PN junction. Moreover, the drift cannot be controlled, so it is only the diffusion that is controlled, and diffusion is controlled by changing the voltage that is applied across the junction. Okay, after studying these basic things, we also tried to understand some applications of the PN junction, and one of the applications is the solar cell. One real life application where this is very important is solar cell, and second, uh, one of the most important real life applications is an LED, light emitting diode, because as you might have also realized that LED is one of the most important uh, lighting. It is one of the most important constituent of lighting and display systems nowadays. So it has huge application in modern times, and we try to understand the basics of these devices. So this is the point where we finished the discussion, and this is sort of the device aspect of the diode. This is how the diode or PN junction device, solid state diode or a PN junction device looks like. But in most of the cases, or in many cases, diodes are used in circuits as well. And uh, so here we'll quickly go through the circuit model of the diode. And in circuits, we are mostly concerned about the IV characteristics of the diode. Okay. So in circuit applications, circuits, whenever we have a complicated electronic circuit, diode is sitting somewhere in the circuit. Generally, it is assumed that when the diode is reverse biased, then the diode is off, which means that there is no current that is flowing through the diode, whatever be the voltage on the diode, unless the voltage is extremely high so that it is creating a breakdown in the diode. So until breakdown, the diode is assumed to be switched off, just like that. Okay. And in the forward bias in circuits, generally uh, it is, and this is also clear from the characteristics of the diode, that for up to, let's say, in the case of silicon diode, up to 0.7 volts of forward bias, the current is extremely small in the diode, and the current abruptly increases beyond this voltage, and that's why we see this kind of exponential peak in the exponential trend in the characteristics. So yeah, so if the diode is somewhere in the circuit, then generally the way the diode is modeled is, one of the ways is like this. Uh, Let me take the yeah, one of the ways in which diode is modeled in a circuit is like this. So according to this characteristics, as you can see, the diode current is 0 up to a forward bias voltage of 0.7 volts. So for all voltages that are less than 0.7 volts, the diode is switched off as if it is an open circuit. There is no current flowing through the diode, whatever be the voltage applied. Okay. And as soon as the voltage reaches 0.7 volts, the diode is turned on and it behaves like a short circuit. Okay, so this is one of the most popularly used diode model in circuits. And this is true for the silicon diode because this 0.7 volts is the cut-in voltage of the silicon diode. And generally the ideal diode, the ideal semiconductor diode is the one in which uh, for voltage less than 0 volts, it is turned off. And as soon as the voltage reaches above 0 volts, it is turned on. So switch on for positive voltages and switch off for the negative voltages, or short circuit for the positive voltages and open circuit for the negative voltages. So this is the ideal diode model. This is generally the uh, whenever it is specified in any question that assume the diode to be an ideal diode, in that case just take this characteristics of the diode. Otherwise, if you are given, if you are, it is said that it is a silicon diode with cut-in voltage of 0.7 volts. Generally, this model of the diode is used. So as you can also see here, a silicon diode is the ideal diode, as if there is an ideal diode, and there is this 0.7 volts battery in series. So before 0.7 volts, the net voltage across the diode is negative and it is switched off. And as soon as the voltage reaches above 0.7 volts, the net voltage across this diode is positive and it is turned on. It is switched on, or it becomes short circuited. But generally, so these are very, I would say, approximations, ideal approximations. But generally, there is a resistance of the diode as well, as you can see, and the resistance can be obtained by taking the slope or by calculating the slope of this plot. And this resistance is generally called as the average resistance of the diode. And uh, in the piece, so this model is somewhat more realistic for the silicon, for any diode, I would say. And in this model of the diode is assumed to be turned off for all voltages less than the cut-in voltage. And as soon as the voltage reaches above the cut-in voltage, it is assumed to be a linear IV characteristics with resistance R average, which is calculated from the actual characteristics of the diode. Okay. So this is known as the piecewise linear model. This is known as this is also a realistic model, and this is known as the ideal model of the diode. Okay. In the piecewise linear model, the diode is assumed to be, or the diode is modeled by an ideal diode in series with a resistance or average resistance and a battery. Okay. So, so finally, what we can say is that the diode can be in circuits, the diode can be modeled by any one of these three things, any one of these three characteristics. This is the most realistic one. This is slightly ideal, more frequently used, and this is the ideal model of the diode in which is used whenever there is it is not specified what is the cut-in voltage. So for qualitative analysis, generally the ideal model is used. Okay. So whenever you see a diode in circuit, depending on the situation, any one of these three models can be used. This is the most accurate one. This is slightly less accurate, and this is an ideal model of the diode. Okay, and this is very basic stuff. So no big thing here. Any question in this?
R average and cutting voltage are sir are of diode. Na?
Yes, yes, for the diode. So for silicon diode, the cut-in voltage will be uh, 0.7 volts, and our average is few tens of ohms. But
Okay.
Sir,
So
why we have
slope will
written
give
ideal diode?
1 by R average.
okay,
Sir, why we have written diode to be ideal in the second diagram?
this one or this one?
Sir, in the
This
right
upper one,
side. In the right side, there are
this
three
one.
diagrams. Sir,
Okay,
in these
yeah,
diagrams, second one.
this one.
Yes,
Yeah,
sir.
so generally, yeah, so let me sort of tell you that generally, whenever, so this is the symbol of the diode, all of us know this, okay?
Yes, sir.
And generally, whenever this symbol is used in circuits, it means an ideal diode, okay? It means that uh, that 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 for positive voltages, this is short circuit, and for negative voltages, this is open circuit. So for a real diode, the model will be that there is an ideal diode, and in series there is a resistance and there is a battery. This is known as the piecewise linear model of the diode. The second model, that is slightly less accurate and more frequently used, in which we do not consider the average resistance. In that, the diode is modeled by an ideal diode in series with the this voltage battery, the cut-in voltage battery. So this ideal diode is written. It means that this symbol is, in most of the cases, this is used for ideal diode. So whenever this symbol is given in the circuit and nothing is said, then it means that we are considering an ideal diode.
Okay, sir. Okay.
Okay, so these models will help you to solve electronic circuits, to calculate current and voltages across various components in electronic circuits if we approximate a diode by these characteristics. Okay, in 80% of the cases this is used, ideal diode case is used, but when we want to be more accurate in real world applications, these two models would be preferred. So this essentially, this concludes our discussion of the PN junction and diodes. And we spent a lot of time in discussing this. Now, the next, or I would say the most important electronic device is a transistor. And I hope that nobody would argue that. In fact, a transistor is uh, by some people it is called the most important invention of 20th century. This is the most important uh, invention of the last century, actually, because if you look at the electronics revolution in our lives, and even computing revolution in computing technologies, or for that matter, every engineering branch, that is because of the development of the electronic systems, and that is to a great extent because of the discovery of the transistors. Okay, but if we understand diode or PN junction properly, then understanding the transistor is not a big deal. And that's why with the background of the diode, now we are in a position to start discussing the transistors. So anybody knows what is the meaning of the word transistor? Anybody here is aware of this?
Transfer resistance.
Yeah, can you explain this? What do you mean by this?
So because resistance is changing with the current we are passing to the transferring to the base. So if
We are
current is
transferring to
0 to
the
the base, so like when current to the base is 0, then resistance is infinity between collector and emitter. And when like the base is saturated, then it is like short circuit. So it is like uh, resistor. We can model it like a resistor.
okay, but why this transfer word is there? Why? Yeah, you're right. It is sort of a resistor in a way. So that explains why this ester is there. But why is this trans is there?
Sir, maybe because we are transferring current from a region of low resistance to another region of high resistance, so that power amplifies.
Okay, but how do you know that we are transferring the current from a region of low resistance to high resistance?
Sir, that depends on the biasing of the transistor.
Okay, so you are talking about the BJT transistor. Is that right?
Yes, sir.
Okay, yeah, yeah. So you are right. You are right to an extent that one explanation or one root of this word is goes to the fact that in bipolar junction transistors, the current is transferred from a region of low resistance to to a region of high resistance. So we are transferring the current across uh, variable the resistance region, and that's why this is known as the, or by combining this transfer and resistor word, this transistor word came up. Yes, anybody else
One,
has to say anything? Yes. Yeah.
so can you repeat that trans importance? Why trans is there?
Yeah. So as one of you told that uh, that in particularly in BJT, bipolar junction transistor, the current is transferred from a region of low resistance to a region of high resistance. Okay, so the current is transferred across resistors. So that's why these two terms are combined to explain this device. Although uh, that is uh, yeah, that is assumed to be the root of the word transistor by many people. But the transistor word actually came up in Bell Labs, and uh, so when this point contact transistor was discovered in 1947, December 1947, then there was a voting in Bell Labs on naming this new device actually. Okay, and uh, one of the reasons that and finally this name transistor was selected, and one of the reasons that was given to choose this name was that this transistor is pretty much like a triode, so vacuum tube triode. It had three terminals. It could achieve amplification and switching. And in triodes, this transconductance is extremely important. Transconductance means, or transconductance implies the effect of the third terminal on current between the two other terminals. Okay. So, and it seems that the Bell Lab at that time was naming devices with this suffix "ister." So they just invented, they had invented a varistor and thermistor few years back. So that's why this new device in which we could have a transconductance or a control of third terminal on current between the two other terminals. This was named as transistor. Okay, so this is given as the reason behind naming this device as transistor. Although some people who were in that voting, some employees of Bell Labs, some scientists in Bell Labs who were in that voting, they had different reasons of naming this device as transistor. Yes, can you please?
Hello?
Can you please?
Ah,
Yeah. So the official region or the officially it was the reason that I just explained to you. It was given, but when different employees were asked, they gave different reasons, and some of them told that this device could transfer current from low resistance to high resistance region. That's why they thought that this name would be better. And some said that it had good transconductance or good trans resistance. That's why this transistor name was suitable. Okay, so this is a bit of history around the name transistor. Finally, in a nutshell, what we can say is that a transistor is a device, a three-terminal device in which the current between the two terminals can be controlled by the third terminal. So there is this transconductance in the device, and that is the original root of the word transistor. And this device, a transistor is generally defined as a device which can achieve amplification and switching. Okay, so these are the fundamental operations that can be done using a transistor. One is the amplification and second is switching. And generally there are two transistor actions, I would say, or there are two ways to achieve amplification and switching. One is used in BJTs and second is used in FETs. And so this ways of achieving amplification and switching is known as the transistor action. And the first transistor action or the transistor action 1 is something like this. And one of you has already pointed it out that in this device we have a region. In this device we have a region where there is a resistance, small resistance R, and if we apply input voltage across this resistor, a current I will flow through the resistor. And in this device, this current I can be transferred to a high resistance region. So if the same current flows through a high resistance, capital R now, so the voltage that we will obtain is the V out. So that way, if you if we can sort of see by doing simple calculations, uh, input voltage is Vi, current is I, and small r is the input resistance. So Vi is I times small r, and the output voltage is Vo. Current is the same I, and the output resistance is capital R. So Vo is capital I times R. So if we divide this second equation by the first equation, Vo divided by Vi will be capital R divided by small r. And if capital R is larger than small r, in that case, output voltage is more than the input voltage, which means we have achieved amplification. Okay. So is this sort of clear? This kind of
Yes.
this is a very simple thing. You guys might be already aware of this. And in a BJT, in a bipolar junction transistor, this small resistance is the forward bias junction, because as we have seen that in a forward bias junction, uh, the resistance is less as compared to the reverse bias junction, because if you see these characteristics and if you try to calculate the resistance here by taking the slope, uh, this will be the resistance will be small here as compared to the resistance here. So, so finally, the transistor is a three-terminal device, and in which the current through two terminals can be controlled by a small change in current or voltage at the third terminal. Okay. In BJTs, generally the current between two terminals is controlled by the current on the third terminal. And in FETs, the current between two terminals is controlled by the voltage applied at the third terminal. Okay. This control by the third terminal, actually, this gives us this amplification capability of the transistors. Because if we apply a small AC signal on the third terminal, then this small signal is reflected as a big signal on the two other terminals. Okay, and moreover, apart from amplification, and as one of you has already pointed it out, that if we do not apply any current or any voltage on the third terminal, the current between the two other terminals will also be zero. So which means that the transistor will be switched off. And if we apply a proper amount of voltage or current on the third terminal, there will be a finite current in the transistor between the two other terminals. So that way the switching is also achieved. So finally, what we can say is that transistor is a three-terminal device, can achieve amplification and switching. And one terminal controls the current between the two other terminals. And one of the ways in which it is done is like this. As we have seen that if the current is transferred from a low resistance part of the device to a high resistance part. Okay. This is generally the case with BJTs. This is how a BJT works. In BJT, the current is transferred from a forward bias junction to a reverse bias junction. A forward bias junction is a low resistance part of the circuit, and a reverse bias junction is a high resistance part of the circuit. And that way, this amplification is achieved. Okay. Now, coming to the second way in which the transistor action can be achieved, which means the switching and amplification can be achieved. The way to understand this is, yeah, let's consider the transistor to be a black box for a moment. So let's say that this black box is a transistor, and we have not shown the third terminal of the transistor yet. We are just showing the two terminals through which the current will be flowing. Okay. So please remember that we have not gone into the specifics of the transistor yet. We have not discussed how a BJT or a FET looks actually looks like. We are just discussing the transistor operation in an abstract way. Okay.
So you are not
So So let's consider the transistor to be a black box device, and the two terminals through which the current is flowing are these terminals. And let's say that we have applied a battery across this transistor. The battery voltage is E and the series resistance is capital R. Okay, and so in this, if we apply KVL, voltage, Kirchhoff's voltage law, then you can see that that E is equal to ID times R plus VD, where this ID is the current through the transistor and VD is the voltage across the transistor. This is ID is also the current through the circuit. Okay, this all right. This is simple KVL equation that satisfies this circuit constraints. Now, this ID is the current through the transistor and VD is the voltage across the two terminals of the transistor. The transistor has its own IV characteristics. Okay, so there is a particular relationship between ID and VD in a transistor. So, so this first equation, this KVL equation, this is also known as the load line equation of the circuit. So if we plot ID versus VD, okay, ID on the y-axis, VD on the x-axis, if we plot this first equation, then you would see that that the intersection on the y-axis will be E by R and the gradient of the line will be minus 1 by R. Okay. So this will be the line that will satisfy this KVL equation. And then there is a transistor IV characteristics relationship between the current and the voltage in a transistor, and generally this is how it looks like. This is how it looks like in MOSFETs, field effect transistors. And the intersection of these two equations or intersection of these two plots will be the point where this circuit will be operating. So at the intersection, the current and the voltage will be there in the circuit. Now this point is clear or not? If not, please.
Sir, what will the intersection define? Sir, what will be it determine in the diagram?
So this line is the line that satisfies the KVL, this load line basically. Okay, and this non-linear curve, this is the device characteristic. This is the characteristics of the transistor. This is how the current and the voltage of the transistor are related to each other. Okay, so the intersection of these two plots will be, so will give a current and voltage value essentially. So this current and voltage value will be the value that will be there in the circuit. So the circuit, actually this circuit needs to satisfy two constraints. One is the load line constraint and second is the this device constraint, and the intersection of these two constraints will be the solution for the current and voltage in this circuit. Is this clear?
Yes, sir. Clear.
Any other question here? So okay, so here we have not yet considered uh, the third terminal of the transistor. We are just we have just considered the two terminals of the transistor, and the transistor is assumed to be a black box, so to say. Now let's introduce the third terminal here. Okay. The third terminal, generally known as the gate terminal, and we can apply some voltage on the gate terminal as well. And this device characteristics ID versus VD will change with the gate voltage as well. Okay. So now, as you can see that apart from these two terminals, we have applied a voltage source on the third terminal as well. And for different voltages on the third terminal, this is how the characteristics will be changing. So when the gate voltage is 0, this is the IV characteristics of the transistor. But as we know that this third terminal is the control terminal, it can change the current between the two other terminals. So if we increase this gate voltage slightly, so this is 0.25, this is how the characteristics will change. At 0.5 volts, this is how the characteristics will change. And similarly, at 1 volts, this is what will be the IV characteristics of the transistor. Okay. So now is the interesting fact. At any gate voltage or at any gate voltage. So for example, if we are considering 0.5 volts, this curve, the intersection between the load line and this plot will give us the current and voltage in the circuit. All right. Is this point clear?
Yes, sir.
So the intersection between this line and these plots will be the valid solutions for different gate voltages. Now, let me ask you something. If we change the gate voltage, let's say from 0 volts to 0.5 volts, what would be the change in the VD, this VD? Just take a moment and try to answer this. If in this circuit, initially the gate voltage was 0 volts and suddenly we change it to 0.5 volts, what would be the change in the VD?
So it will decrease.
Sir, 5 volts.
Decrease by 5 volts.
Sorry, the last one I could not hear.
So VD will decrease by 5 volts.
Yeah, so you are right. It is around 5 volts because for when the gate voltage is 0 volts, this is the point of intersection and the VD corresponding to this point is around 10 volts. Okay, very close to the 10 volts. And if the gate voltage is 0.5 volts, the point of intersection is this, and here the VD is around 5 volts. So a 0.5 volts change in the gate voltage is producing a change of around 5 volts in the drain voltage or in the VD. Do you see this? So if we have a black box device like this, in which the characteristics of the device, the IV characteristics can somehow be like this, like these nonlinear lines. In that case, a very small change of voltage on the third terminal is producing a large change in voltage on the voltage between the two other terminals. Now, is this point clear or not? Yeah, is this clear, everybody?
Yes.
Yes.
Yeah, so this is the basic amplification operation of the transistor. And this is the case with the field effect transistors. In the field effect transistor, the MOSFETs, generally the IV characteristics of the device looks like these lines. And if we put that transistor in a circuit, then as you can see that a small change of gate voltage can bring large change in the drain voltage, and that's why we can say that this amplification of in the voltage is achieved. Although there is by amplification, we do not mean that new energy is being created. The transistor is not a power generating device. It's not an active device, so to say. It is not producing power, it is consuming power. This amplification is achieved with the help of these batteries basically, especially this battery here. Had this battery not been here, in that case, we would not have changed the voltage from 10 volts to 5 volts. So we are not generating net power in the circuit, but what we are doing is with the help of batteries, we are if we apply a small AC signal on the gate voltage, and if the AC signal fluctuates between 0 to 0.5 volts, this the signal across this transistor, this VD signal will fluctuate from 5 to 10 volts. Okay. So by applying a small AC signal, we have produced a large AC signal. So this AC amplification is there, but it is not producing net power. It is still using the power of the battery. It is producing an AC amplification in the circuit. Okay. So this point should be very clear because this might create conceptual confusion that a transistor might be supplying a net current or a net power. Okay, is this all right?
Yes. Sir. Is
Yeah,
in reverse
yeah.
bias.
Your
This
your voice is not proper. Can you please speak?
now, sir.
It's better. Yeah, yeah. Try speaking.
Sir, is in reverse bias. We also get same graph, or we get something different.
Sorry, in reverse bias.
Reverse bias. Yes, sir. If here we transistor, sir. We put transistor in sir forward bias. No? If we put the transistor in reverse bias, then what happens?
So I guess you are confusing. There is a confusion between the diode characteristics and this characteristics. This at the moment we have not gone into the details of the transistor. We are just considering. We are just assuming that if we can somehow create this kind of characteristics, these lines, then we can achieve amplification. But when we discuss or when if you go back and study the MOSFETs, there are some MOSFETs, for example, the P MOSFETs generally, which will work with negative voltages, and the N MOSFETs will work with positive voltages. Okay. So
Okay, sir.
MOSFET is
Thank you.
not like a simple PN junction. It is a more complicated device. So it is we cannot say that there is like diode. There is no simple forward bias and reverse bias because there is no single junction. There are many junctions actually there. Okay. So yeah, so this is the basic mechanism of amplification in the, especially in the MOSFETs. The mechanism of amplification in BJTs is like this. Okay, so these are two types of transistor actions that are there, and they are implemented in two different kind of transistors, one in BJT and second in MOSFET. So now we will have a look at these two kind of transistors, the BJT and the MOSFET. Up to this point, we did not go through the details of the devices. We just had an abstract discussion on the transistor. Okay. So as we have discussed during the history part that the first transistor was demonstrated in 1947 and it was a point contact transistor which looked pretty similar to a BJT. Finally, this transistor was improved in a BJT, and this is how a bipolar junction transistor looks like. There is this transistor, the bipolar junction transistor, as the name says, it is a junction transistor. It means that it involves PN junctions, and bipolar means that. What does bipolar mean, by the way? Anybody knows? The root of the word bipolar here?
Sir, it's just having two opposite poles. That's what bipolar means.
No, but what are the two poles here in the transistor? Anyone else?
So two side have p side semiconductor.
Sorry, please repeat.
So two side have p side semiconductor E and C. Two at E and C.
Yeah,
So
there
hence
are
call
two
it
types.
yes, sir.
Okay, yeah, that is also not the reason, properly the reason. Bipolar means that that the current in this transistor or this transistor action is performed by both electrons and holes, which means that both polarity of the charge carriers, so electrons are negative polarity charge carrier, holes are positive polarity, and both electrons and holes participate in this transistor. They, in order to achieve transistor action in this transistor. Okay, so generally in semiconductor devices, whenever both electrons and holes are play central role, uh, then those devices are known as the bipolar devices. And if only, for example, in MOSFETs, either electrons or holes, only one polarity of charge carriers is important. So those kind of devices are known as the unipolar devices.
So sir, diode is also bipolar.
Yes, diode in a way is also a bipolar actually. And this BJT is also quite a general, quite an extension of the diode itself, because as you can see that it is a diode, PN diode, and if we put one more P type on the other side of the N type, it becomes a BJT. FET, so yeah, that this is one of the main differences between BJT and MOSFETs. Are generally unipolar devices, and BJTs are the bipolar devices. So now let's quickly see now, since we have a background of current conduction in a PN junction, we can, I guess, understand the mechanism of a BJT as well. So there is this one kind of BJTs can be when there is a P-type material on two sides and N-type in the middle. Another type of BJTs can be NPN, where a P-type semiconductor material is sandwiched between the two N-type materials. So these two kind of transistors can be there, BJTs can be there, and generally in the most frequent operation of this transistor, BJT transistor, one PN junction is forward biased and the other one is reverse biased. So for example, if we take the case of PNP BJT, generally while we want to achieve amplification, in that case, the first PN junction is forward bias and the second PN junction is reverse bias. Uh, the convention is that the left terminal of the transistor is known as the emitter terminal, middle one is the base terminal, and the right one is the collector terminal. And there are important differences between these three terminals. In an actual BJT, generally the doping of the emitter is more as compared to the collector. So they are not symmetric in that sense. And base region is very small and lightly doped. So emitter is the most heavily doped. Base is the smallest and lightly doped. Collector is large, like emitter, but lightly doped. And if this first junction, this emitter base junction is forward bias, then what would happen if we just consider this the first junction? This is a simple PN junction and it is forward bias. It means that a positive voltage is applied on the emitter and a negative voltage is applied on the base. And what happens in forward bias, if you recall from our earlier discussion on the diode theory, the diffusion of charge carriers is high. Yeah, it means it behaves like a short circuit. That is from the from the circuit perspective, but from the charge carriers perspective, the diffusion current, the majority carriers diffusion is increased quite significantly. All right.
Okay, sir.
So it means that from the P side, the majority carriers are holes. They will be diffused heavily to the N side. And in the N side, the majority carriers are electrons. They will be diffused to the left side. So there will be a lot of holes that will come from the emitter to base when this is forward biased. And the electrons in the base will travel towards the emitter. This is the diffusion component of the current, and there will be a small drift component as well. In the drift component, the minority carriers are drifted across the junction. And the minority carriers in the P-type material are electrons and minority carriers in N-type are holes. Okay. Now, so this is the case. The majority carriers primarily will be moving across the junction, which means that a lot of holes will be traveling to the base side. Now, if this second junction is reverse biased, this collector base junction is reverse biased, what happens in a reverse biased junction?
So drift current increases.
Yeah, or in other words, what happens is that the diffusion current is suppressed and the drift current is the only current that is there. So generally the drift current does not increase significantly, but the diffusion current is suppressed very much. So in that case, what happens is that in the reverse bias junction, all the minority carriers that are there close to the junction, they are swept through the junction. Now, something interesting happens here, and maybe you already know this. Because of this forward bias, these holes are the majority carrier in the p-type, but as soon as they enter the n-type material, the base part, they become the minority carriers. And because of this reverse bias, these minority carriers will now be taken to the other side, because uh, in the reverse bias, only the minority carrier current is there. So cumulatively, what happens is, because of the forward bias in EB junction, emitter base, lot of holes are sent to the base side, and because of this reverse bias in collector base, these holes will be taken to the collector side. Because these holes, the holes coming from the emitter side, they become minority carriers in the base uh, terminal, the base part of the transistor, and they will be swept to the collector side. Is this clear?
Yes, sir.
Yeah. So this is what is happening. This is the interesting part of the BJT, and that these holes are sent from the emitter to the collector via base, and base becomes like a controlling terminal in this case. So there is a current between the emitter and the collector. Now the question is, how is the base a control terminal? Right? So I will let you think about it, and in our next uh, extra session, we will finish the discussion of BJT, also the MOSFETs, and then there is one more thing that we need to discuss, and that is the some important electronic circuits. And those electronic circuits are like oscillators, op amps. Okay, so those things are also important. So that's what we need to we would need to discuss in the coming sessions. Okay, so that's all for the day. If you have a question, please ask.
So what is double E here? V double E.
Double E is the so generally this battery that is put between emitter base. This is represented by EE. Just to emphasize that it is applied on the emitter terminal. So this E comes from the emitter terminal. Similarly, this C comes from the collector terminal. So this is the voltage of the battery. The battery voltage that is applied on the emitter base junction is denoted as VEE, and the battery that is applied across collector base is VCC. This is just a convention.
Okay, sir.
Okay.
But is there an importance why it is repeated one like EE and CC?
Yeah. So I would say I'm not sure what is the reason, but this is generally the convention in transistors that. So
So why
what
not
happens is,
PPE?
yeah, you are right, but the VEB might create a bit of confusion actually, because that way it will this uh, this point that so sometimes what happens is that there is no battery that is applied across VEB. Sometimes what happens is we apply a voltage on the emitter terminal, and the base terminal is connected to other part of the circuit. Okay, so there is a voltage source that is just connected to the emitter terminal, and that way this EB junction becomes forward bias. Similarly, a voltage source is only connected to the collector terminal, and base is sometimes grounded or sometimes it is maybe connected to the other circuit. So, so in that case, this VEB will be confusing because it might not be connected to the base terminal as well. It might happen that base is grounded and emitter is only, the battery is only connected to the emitter terminal. And this is also the convention in MOSFETs actually. So like BJTs, MOSFETs have source, drain and gate terminals, 3 terminals. And generally the battery that we connect on the drain is represented as VDD. And the reason for that is that the source is grounded and only the voltage is only applied on the drain terminal. Okay, so that I think that this convention comes from that fact. But I would say that I have not gone into the roots of this convention, but that's what my understanding is. Okay. Any other question?
In middle wire, two types of current flow.
Sorry, in
Middle wire, common wire.
yes, in the base part, in the base terminal.
Yes.
This base terminal, you are saying that two types of current flows. Is that what you are saying?
Yes, sir.
Yeah. So generally, everything is about electron movement actually. So if we are saying that the holes are moving, it means that electrons are moving in opposite direction. And if we are saying electrons are moving, then electrons are moving in that direction. So generally, it is only the electrons that are moving through the wires. Okay, because hole is not an actual particle; it is just it is a quasi particle, so to say. It is a model of it is a mathematical model of vacancy in the system. So ultimately, it is electrons that travel physically in the system. Okay, is this clear or do you want more elaboration on this?
So it's clear.
So I would recommend you to go through the basic mechanism of BJTs and also the MOSFETs. It would be an interesting read, I'm sure. And uh, so since we do not have too many classes, so maybe from next class onwards, I'll be a bit quick in discussing these things. Otherwise, I may not be able to complete everything that we want to do here. Okay. So that's all for today. And
Okay,
I'll schedule, yeah, another class
thank
in
you, sir.
consultation. Yeah. Okay. Yeah.
Thank you,
Thank you.
sir.
Thank you. See you.
Thank you, sir.
Yeah. Bye bye.
Thank you, sir.
Thank you, sir.